my biggest advice for related rates is it comes down to three things. Number one, know the volume or surface area, or know your geometric equations, or know the equations of shapes and 3D shapes that you learned from geometry. So, for example, the volume of a sphere is 4/3 pi r cubed. Um, Area of a triangle is 1/2 base times height cube. The area of a cube is just the length cubed. So just there's a whole variety of equations for different shapes. I highly recommend memorizing or learning a lot of them because most related rate problems you'll have to deal with shapes. Actually, all related rate problems have to deal with some triangle or some 3D um, shape. And my second tip is write down everything that you're given in the problem. So write down given information. It's very, very, very important to write down everything you know and what you don't know or what you're trying to solve for so that you can keep track of what you need to do. And my third tip is always draw a picture. Pictures help a lot. So all related rate problems, or pretty much all of them, not all of them, but a lot of them have to do with some picture, a sphere increasing or a person walking or boats moving. So always draw a picture. It'll help you out a lot. Unless you draw the wrong picture, then you're screwed. But yeah, those are my top three tips. And the only way to get good at these is if you do them over and over again. There's only a certain amount of problems you're more likely to see on your tests. So just practice, practice, practice. It's the only way to get better at letter rates. Nothing new is really introduced. It's just applying the chain rule, product rule, maybe even quotient rule, and other rules. And it's basically just word problems. So yeah, good luck. Well, our first problem, we have the length of a right triangle is decreasing at a rate of 5 inches per second. The height of the right triangle is increasing at a rate of 7 inches per second. And if the length of the right triangle is 8 inches and the height is 6 inches, A, at what rate is the hypotenuse changing? B, at what rate is the perimeter changing? And C, at what rate is the area changing? So we're going to do A first. And for our first step, let's write down everything we know. When you're doing related rates, it's very important to write down all the numbers and rates are given in the problem. So let's start here. We know the length of the triangle is decreasing at a rate of 5 inches per second. So the derivative of length with respect to time is, and because it's decreasing, we're going to have a negative 5 inches per second. The height of the right triangle is increasing at a rate of 7 inches per second. So the derivative of height with respect to time is 7 inches per second. And we know the length of a right triangle is equal to 8 inches, and the height is equal to 6 inches. So for our first question, for our first part of the problem, we're asked to find the rate at which the hypotenuse is changing. So the derivative of the hypotenuse with respect to time. So let's call the hypotenuse x and say we don't know x, and we also do not know the rate at which x changes. So we have everything we're given so far. We don't know the hypotenuse or the rate hypotenuse changes. So let's draw our triangle. So this is our right triangle. For the first step, let's figure out x. So the length is 8 inches, the height is 6 inches, and we do not know the hypotenuse. If you guys remember, for a right triangle, we can use a squared plus b squared equals c squared. What's that called? We can use Pythagorean theorem. So in this case, a squared plus b squared equals c squared. For the sake of this problem, L is going to equal A, so we're going to have L squared plus, and then B is going to equal H squared, and then C is going to equal X. So we know the values of L and H, but we do not know the values of X, so let's plug in what we do know. L is 8, so you have 8 squared plus H is 6, plus 6 squared equals X squared. 8 squared is 64, 6 squared is 36, and we have x squared. If we add these together, we get 100 equals x squared. Take the square root of both sides to get x. The square root cancels out with x squared, and we're left with x equals 10. So now we know that the hypotenuse is 10 inches, so we can write that here. 10 inches. Now, if we want to find the rate at which the hypotenuse changes, we need to take the derivative of the Pythagorean theorem with respect to time. So now I'm going to write in the triangle all the different rates. So the rate at which the length decreases is -5 inches per second. The rate at which the height increases at 7 inches per second. And we do not know the rate at which the hypotenuse changes. So we're just going to take our normal equation that we had last time. We had L squared plus H squared equals X squared. Now we're going to take the derivative of both sides of the equation with respect to time. So the derivative of 2, so we have the derivative of the left side of the equation, we're going to have 2L times dl dt. This is just chain rule stuff. We'll have 2h multiplied by dh dt equals 2x dx dt. If you don't know how I got from here to here, basically, if you take the derivative of something with respect to time, the variable is not time, it's just like taking the derivative of x squared equals 2x. But if you take the derivative of something like y squared with respect to x, you're going to get 2y multiplied by dy dx. So this is essentially what I'm doing for this equation. Now let's plug in what we have. So wait, first let's factor out a 2 because we can divide. So we're left with L times dl dt plus h times dh dt equals x times dx dt. And we're solving for dx dt. So let's plug in everything else we do know. The length is 8, so we're going to have 8 times the derivative of length with respect to time. We're given it's -5 inches per second, so we're going to put -5. Height is 6 inches, so we're going to put 6 in for h. And the derivative of height with respect to time is 7 inches. And we know x is 10. We just calculated x not too long ago. And we do know, all we need now is dx dt. So let's rewrite the equation. Now, this is simple algebra using a solve. So we're going to have dx dt, or the rate at which the hypotenuse changes, is equal to 8 times -5 plus 6 times 7 all over 10. And this equals 0.2 inches per second. So -40 plus 42, 2 over 10 is 0.2. So that is the rate at which the hypotenuse is changing. So we could put that over here, 0.2 inches per second. And that's our answer for A. Now let's do B. So now I want to find the rate at which the perimeter changes. So in order to do this, we have to know the perimeter, what the equation for a perimeter of a triangle is. So perimeter of a triangle equals the length plus the width plus, the length plus height plus hypotenuse. So let's take the derivative, because we're trying to find the rate at which the perimeter changes, so we need to take the derivative of both sides with respect to time. So we're going to have dp over dt equals the derivative of L with respect to time, it's just dl dt, with h is dh dt, and for the hypotenuse, it's dx dt. And we know all these values, so let's plug them in. So we don't know dp dt, but we do know dl dt to -5, so we have -5 plus dh dt is 7 plus dx dt is 0.2. And if we add these together, we should get dp dt, so -5 plus, we get 2.2, or yeah, we should get 2.2 inches per second. This is the answer for part B.
And I have not eaten anything today, so I
Oh, bummer. All right, for part C, we're gonna find the rate at which the area of the triangle increases. So for the equation for the area of a triangle is 1/2 length times height, or base times height. In our case, it's gonna be length times height, so we're gonna have L times H. So if we want to find the rate at which the area increases, we have to take the derivative of the area with respect to time. So we have dA dt equals 1/2 times, and then for L times H, we're gonna have to use the product rule to find the derivative. So we're gonna have L prime times H plus H prime times L. This is just equal to dL dt times H plus dH dt times L. So now we can plug in what we know. We know dL dt is -5. You know H height is 6 inches, and dHdt is 7, and length is 8. And don't forget the half here. So we have 1/2 times -35 plus b6. We're going to get 1/2 times 26, which equals 13. So the rate at which the area is changing is equal to 13. And the units for this are going to be in inches squared per second, because we're dealing with area. Units are pretty important. And this is the final answer for part C. For our second problem, we have a Connell cup is 4 centimeters across and 6 centimeters deep, and water leaks out of the bottom at a rate of 2 centimeters cubed per second. And how fast is the water level dropping when the height of the water is 3 centimeters? So let's start by drawing our Connell, or our cone cup. And we're given that it is 6 meters, or sorry, 4 centimeters across, and it's 6 centimeters deep. So the height is 6, the diameter is 4, so h is 6 centimeters, the diameter is 4 centimeters. And we're given that the water leaks out of the bottom at a rate of 2 centimeters cubed per second. So we have dV dt equals, and because it's leaking from the bottom, we're going to have a negative sign in front of the rate, and we're going to have 2 centimeters cubed per second. And we're trying to find how fast the water level is dropping when the height of the water is 3 centimeters. So let's try another. This is just basically water, and this height right here is 3. So for now, we'll put height 2 equals 3 centimeters. So let's write down the equation for the volume of a cone. So we know the volume of a cone is 1/3 pi r squared times height. Now, we don't have the radius right now, but we know that the radius is half of the diameter, and we're given the diameter is 4, so the radius is going to equal 2 centimeters. And let's cross this out. Up here, we'll just write the radius is 2 centimeters. But we don't even want the radius because we're not in the entire problem itself. We're not given the rate at the risk the radius increases or anything. But we're so because we're not given a radius, we want to change everything to h because we're trying to find the derivative. We're trying to see how fast the water level is dropping when the height of the water is 3 centimeters. So we need to find dh dt. But we can't, if we take the derivative of this equation, we'll be left with dr dt and dh dt, but we only want dh dt. So we have to get this r squared in terms of h. So from this original expression here, we know that the ratio between height and radius is 6:2, or 6 over 2, or 3. So 3 times the radius equals the height. So in this case, 3 times 2 is 6. The height is 6, the radius is 2. Now, let's solve for r here, and then we can plug it back into this equation. So we're going to divide both sides by 3, and we're going to get r is equal to h over 3, or the height over 3. And we can plug this back in to this volume of a Cohen equation, because now if we take the derivative of this with h over 3 squared instead of r squared, we can solve for dh dt. So that's exactly what we're going to do. So let's rewrite this as 1 over 3 times pi. And now we're going to substitute r is equal to h over 3, like we just found out. So we're going to have h over 3 squared times h. And we're going to simplify this. H squared, we have 1 3 pi times h squared. It's just h squared. 3 squared is 9 times h. This is going to give us h squared times h is h cubed times pi over 9 times 3 is 27. So this is the volume equation we're going to use to solve this problem. So now we're going to take the derivative of this equation with respect to time. So we're going to have dv over dt equals 3h squared pi all over 27. And we're trying to find how fast, once again, we're trying to find how fast the water level is dropping when the height of the water is 3 centimeters. So for height, we're not going to plug in 6, we're going to plug in 3. So let's do that. So we're going to have, oh wait, also, if you take the derivative of this, there should be a dh dt here. This is what we're solving for. Can't believe I forgot that. Like, if you remember from implicit differentiation, derivative of y with respect to x is just y prime, or derivative of x, derivative with respect to x of y squared is 2y times y prime. Same idea with this equation right here. If we take the derivative of h cubed with respect to time, we're going to get 3h squared times dh dt, and we're trying to solve for dh dt because we're trying to solve for this at when the height is 3 centimeters. So now that we have that, let's plug in 3 for h. So we're going to have 3 times 3 squared times dh dt times pi over 27. And then we're given dv dt in the original equation. We know that's negative 2 centimeters cubed per second, so we're going to make this equal to negative 2. And we want to isolate the dh over dt, so let's multiply both sides by 27 for starters. And then we can simplify this. 3 squared is 9, and 3 squared is 9. 3 times 9 is 27, so we have 27 dh dt pi equals negative 2 over 27. I'm not going to multiply these quite yet because we can get rid of the 27 very soon. So we're going to divide both sides because we want to isolate dh dt. So we're gonna divide both sides by 27 pi to get rid of the pi and the 27. And we're left with dh dt is equal to negative 2 times 27 over 27 pi. Now the 27s can cancel out. Our final answer is negative 2 over pi centimeters per second. So this is the rate. This is the rate. This is how fast the water level is dropping when the height is 3 centimeters. Please like and subscribe or leave a comment under the video if you don't understand something or if I got something wrong, or just leave a comment about what you'd like to see in the future. And thanks.